start this. Congratulations. You made it. You did it. We're doing it. A couple of things. I did have some, well, I tend to keep it, just kind of hang on to it. Whenever I have blank, it's my old calendar. But big pieces of paper. So if anyone wants some big pieces of paper, I think a valuable study tool would be to kind of recreate this decision tree that we introduced for test 2, because of course you're going to have to do hypothesis testing and confidence intervals on the final exam as well. And so, and it might be nice to have some big paper, but otherwise I'll just recycle it. But I do hang on to it for this class at this point in the term. So, or some version of that decision tree, right? Using your formula sheet and just kind of mapping out what type of question is it, you know, summarizing your conditions, because you'll notice that they're all very similar, and that kind of thing. But of course, so this is in week 12 that I had posted it when you were working and practicing for test 2. And there's also the Word document if you prefer, but sometimes just kind of sketching it out by hand is nice. So help yourselves. And again, if you don't have your test, please pick it up, because I don't want them. And it's all going to come back to haunt you in some way on the final exam. You know? Now, let's see here. We are going to do section 8.4, which is for our bonus question on the final exam, of course, as promised. But before that, what I want to do is talk you through this final exam outline. I have posted a practice for the final. Of course, it's, again, really long. All right, more practice. Okay, with the solutions. Okay, and so those are there, including some regression questions. You can tell, how can you tell it's a regression question? Well, because there's a scatter plot. All right, and so there's some regression questions that you can practice as well. Okay. I will say, I think it's one or both of these, how I typeset these solutions. It's possible that the solutions in the background knows more decimal places than it ever showed you. So if your numbers are slightly off, that's probably why. I'll go back and look at that, but if I forget, that's probably why. For the regression questions is the only time it's a problem. Oops, here. And of course, the solutions, blah, 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 blah. So let me screenshot this. Oof, that's loud. Bring it in. Oh, and I still have copies, some blank copies of test 2, if there's anyone who's interested. Might be nice. Yeah, it's by last name.
Oh, sorry.
The test. Did you get your test already?
No.
Yeah.
Would you recommend just doing the final, like the practice for the final, or doing like test 1, test 2, and the final?
Definitely test 1, test 2, the practice for test 1, practice for test 2. I'm assuming that you're gonna kind of work on those. Especially for test 1, there was a lot of kind of background information that I did not put in the practice for the final. And so I think in the practice for the final, I only have like the 5 number summaries maybe and the outliers. But there were some more conceptual things like If you have a normal distribution, then you can use the mean and the standard deviation, that kind of thing. And so it's worth revisiting test one, especially for some multiple choice options. Use it all. I know, not helpful, I guess. Okay. Let's see. I was gonna write it out, but it is on here, so I'll just highlight it. So our final exam is on December 16th from 1 to 4. And last time I checked, we're in E309. Now, sometimes they do change the room numbers, and I'll check closer to the dates. And if there is a change, of course, I'll send out an announcement, but it should be pretty stable. In terms of when am I here? I don't know how those got there. What is my schedule? I'm always available by text or email, of course. And so I am always available by text, which is 250-864-8386, in case you missed it, everywhere on Moodle. That's not a 4. And it's so still no good. Or email, which I assume you have. And so, but in person, I'll be on campus in my office. Now, my office is just downstairs in C104. It's a shared office, and the door is often closed, even though people are in there. So just knock and see, and if someone's in there. But also, the light never turns off. So that's also weird, because it looks like someone's home, even when there isn't. So I'll be on campus in my office on the Monday, December 15th, and of course, the morning leading up to the final exam, and the morning before the exam on December 16th. Can't remember. I don't think I'm on campus. Not on the Friday, I gotta think. So, usually that's kind of when people need my help anyways.
So I have just a question on study habits. For my background, I come from more like a social science background and English background and writing.
Yeah.
So there's a specific way that I know that study for those courses, but when it comes to like math or science courses, I'm having trouble utilizing those study habits for this. So to like really like studying, so like do practice problems and studying constant.
Basically, just do a bunch of practice problems, because then the practice problems are twofold, right? You're practicing that particular problem, but you're also developing a pattern recognition, right? Where you say, oh, I've seen a question that was similar to this, right? And then you remember how to solve that. And then you kind of take those skills and apply it to a similar problem. And unfortunately, the only way to do that is to read a bunch of problems, figure out how to solve them, link them up, and say, hey, these were basically the same. And I know in the beginning, they don't feel the same at all. They all feel brand new. They all feel so different, right? But as you read more and more of them, right, then you'll start to say, oh, this is the same as this one, right? Or this one's the same as this one, right? And I've got those under control maybe, or, oh, I really struggled with, this part, right? And that's also why I post the solutions, so that you can kind of reverse engineer it, because that's how I learn a lot, right? Is kind of reverse engineering. Yeah, if I'm completely stumped, then I look at the solution, I'm kind of like, okay. No. However you learn is not cheating. Yeah, yeah. Good. There's also, and I don't know any of their names. I think one of the, what is her name? Carolina? She's like a study habit coach that they've just brought on new this term. And so if you go to the Learning Center in the library, then I think there's more than one person. I think there's two people whose job it is to help you figure out how to study. So I haven't worked with them yet because they're just brand new, but that might be worth exploring too. Nice. So I will emphasize that these are approximate marks for our final exam, just to give you an idea, because I am upping the multiple choice because we're so late in the term, and I've got, despite the numbers here today, it's actually a really big class, and so I need to get this marking done, and so it's completely self-centered, but usually there's multiple choice anyways. So there's going to be some numerical analysis, so data visualization and summaries, right? So all that test one stuff that you did, you've seen multiple choice questions on that material already, and so that'll be 10 marks. And then there's a contingency table and associated probability calculations, or a tree diagram and associated probability calculations. Now, I am curious whether you prefer the table, where I just give you counts and then I ask you about the probabilities of things, or if you prefer a tree diagram. Usually people prefer the table, which is why that's what it is. I should whisper that into the recording. That's what it is. It's a table. Little ASMR later. Table. So the contingency table, right? Wink, wink. And those answers will be multiple choice. Normal distribution, that's your Z-scores. That's way, way back, right? Those Z-scores. Not even X bar minus mu over S over root N. It's like way, way back. X minus mu over sigma. Okay. And so where we introduced the Z table and talked about, okay, how do I calculate a Z and then find some probabilities, or potentially work backwards, right? From cutoffs, I can find, or from probabilities, I can find the cutoff, right? Working kind of that way. And so that'll be multiple choice, because those are things that we should have under control now, right? And so kind of quick and dirty. And then we have binomial probabilities with the normal approximation. And like we were talking about, because it caught your eye, the Poisson. We didn't do the Poisson, I know, but sometimes we do. And so that's why it's an option, but it's another fake option, I guess. Keep you on your toes, sort of. But then I tell you anyways, so. So that binomial probability with the normal approximation to the binomial will also be multiple choice, roughly 6 marks. What I've decided to do for the conditions for inference, because they're so annoying, is just do 4 multiple choice questions standalone, right? And then for the long answers, I'll just say you can assume that the conditions for inference are satisfied. And you can just do it, right? And so, because that's really what I'm after anyways. So about 4 multiple choice for the conditions, just making sure that you got it under control. Then I made a bold move. A confidence interval question as a multiple choice question, but you do have to write your interpretation, right? So you still have to interpret your confidence interval, right? We're 95% confident that the interval between here and here captures whatever it is you were going to make an interval of, right? And so I still want to see that interpretation, but I don't need to mark your work because I was very pleased with your confidence interval work on test 2. So I'm happy. Oh, and I guess I should do this is from test number 1. And this is test number 2. I'm keeping it vague. It's a chi-squared test, right? Which means it could be a goodness of fit test, or it could be a chi-squared test of independence. I've already tested you on a chi-squared test of independence. Do with that what you will. Then a long answer confidence interval for 7 marks-ish. With the up marks or the higher marks, usually it's about 4 or 5 for a confidence interval. You can expect to have to do that follow-up question of, okay, well, using this interval, what would your hypothesis conclusion be, right? So you're doing confidence interval just like on test 2, right? You had to do it, let's see. Which one was it? Oh, question 1, part B. So expect to have to do that again. Give you a chance to redeem yourselves. Then 2 long answer hypothesis testing questions. I'm not telling you what types, but for each of these long answer questions, you have to tell me what type of question it is for 1 mark. And so that's 1 mark handled, right, for all of these, right? And so kind of chipping away. And so then 2 hypothesis testing questions to finish you off. All right. Finally, a least squares regression analysis for 9 marks. So that's this last chapter that we've been working on. And so things that you can expect, maybe I'll do some options here. These are kind of the potential parts that I could ask you, right? If I give you a scatter plot, then I might ask you to describe the relationship. Right, between X and Y. You have to talk about all 3 things, right? Is it linear or is it nonlinear? It better be linear because that's the only thing that we know how to deal with, right? And presumably we're going to fit a straight line to it. So it better be, you better tell me it's linear, but you have to say it, right? Whether it's strong or weak, right? And if it's positive or negative. Right? So describing the relationship, what else can I make you do? Or what's the next thing I can make you do? There's a couple of different ways that I could give you the correlation, which is what we talked about last day, right? I could, and maybe I'll do it over to the side here. There are 3 ways I could give you the correlation, right? It could be stated, the correlation is this. Or I could give you R squared and you have to calculate the correlation, right? But the correlation is the plus minus square root of R squared, right? So you have to know that. And there's a practice problem in the practice for the final so that you can see what it would look like. And you have to pick the correct sign depending on what the relationship is that you described, right? If it's positive, you have to pick the positive correlation, and if it's negative, you have to pick the negative one. And this one we're not doing, but I could give you, given the covariance SXY, but I'll put a faint line through that because we're not doing that. So either I could state it or I could give you the R squared. Now, if I'm giving you the R squared, I would have to do that quite early on, right? So let's assume that I've stated it, then find the slope. Slope is on your formula sheet, right? So you have to calculate the slope, then interpret the slope. Right, there's 5 pieces of information that I have to give you for a regression question, right? And I think both of those practice problems that I've posted have it just in the sentence, which is what you should expect on the final exam, right? So take some time, practice reading those and mapping them to the right variables, right? Your X and your Y's. Interpreting the slope. For each unit increase in X, we expect a slope increase in the predicted value of Y, right? But I want to see that in a question-specific way, right? Not just X's and Y's or slope, but with the numbers and the variable names. Oops. Then find the intercept. Guess I should say the y-intercept. Right, calculate the y-intercept. Then, any guesses? Interpret the y-intercept. Often I like to throw in, is it meaningful? Right? That's more of a nudge in the direction of, okay, well, what's the interpretation of the y-intercept? The interpretation of the y-intercept is the predicted value of y when X is 0. So really what I'm asking is, well, can X be 0? And you can convince me either way, right? But can X be 0? The line has to cross the y-intercept or the y-axis at some point, right? Just because of how lines are, right? You know how they are, right? But usually it's not meaningful because often X cannot be 0, right? Or it's not reasonable to have an X of 0. Then I ask you to construct the least squares regression line. Or regression equation, maybe. That sounds hard, but what are you doing here? Find the slope. Well, that's, oops, you're B1. Sorry about that. Find the y-intercept, that's B0. You're putting them together, B0 plus B1 times x. Right. Leaving your y-hat and your x open for whatever x you want to put into it. Well, what was the goal of making this line? It was to predict stuff, right? And so, G, use the line that you just made to predict y given some value of x. So predict y given some value of x. Right. And then here, I'll say, beware of extrapolation. Right? Extrapolation is when you're predicting for values or using values that are outside the values of x in your data that you've used to build your line, right? And so extrapolation, it is your best prediction, right? You don't have any other options, but it would yield an unreliable prediction, right? Because you are extrapolating. And so here, if you are extrapolating, then you would get an unreliable prediction. Oops. Oh, and maybe I'll bump that to the same line here. Oh. So sometimes I'll ask you, do you trust this prediction? Right? And so then that's a nudge for you to think about, okay, well, whoa, wait, was I extrapolating or no? If you're not extrapolating, if it's within the range of your x's, then you do trust that prediction. It's a reasonable prediction, right? It's if you're extrapolating, then you would say, no, it's an unreliable prediction because I'm extrapolating. Huh? But wait, there's more. In this scenario, what was the scenario? I gave you the correlation, but of course I need to bring it back to the r squared somehow, right? And so then if I gave you the correlation up top here, right at the beginning, then usually I ask you to find r squared. And r squared is the percentage of variability in y explained by the least squares regression line. By the least squares regression line. Wait. So long. You're going to stop reading as soon as you see some sort of percentage of variability, right? Then you think, oh, that's r squared. Let me just confirm, right? And so explained by the least squares regression line on x. So the question, if I've given you the correlation, would say, find the percentage of variability in y explained by the least squares regression line on x. Then what do you do? If you have the correlation, then you square it, right? And if you want to be proper about it, you can turn it into a percentage by multiplying by 100, but I won't be that picky. Because it's the final exam. The thing about the final exam is I can be a little bit more flexible because there's no more lessons learned here. It's just, did you catch the vision of the course? Did you kind of get the general idea? Right? Tests, there are still lessons to be learned, right? So whether that's, I don't know, encouraging or not, I'm not sure, but there, that's how I see it. All right. Oh, that's what I was going to say. So in the alternative scenario, right, I would have said, 67% of the variability up here somewhere before you have to find the slope, right, is explained by the variability in y is explained by the least squares regression line on x. Find the correlation, right, which means, of course, then you don't want to find r squared, right, because you've already done that part, but I had to pick a lane, so I picked this one. Just kind of the more common one, and it's lots of parts, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 parts, 9 marks. Pretty good. Something's worth 2 marks. I can't remember which one. 1 mark, 1 mark, 1 mark. Maybe I don't get you to describe the relationship. The interpretation tends to be 2 marks. Because that's important, right? The tricky part about stats is I don't really want to spend too much time on the math. It's more about the interpretation, which is what throws people off. Right? It's very important that you take away the interpretation and the conclusions and kind of appropriate wordings. Okay. Any questions about that? All right. Then I guess we're ready for our last little blip here. And we're not going to do the whole section, right? I'll just kind of give you what you need for, as promised, the bonus on the final exam, right? And then we'll just kind of zip through the rest, but don't worry about it. So 8.4, our last section, inference. So that means that we could do confidence intervals or hypothesis testing for linear regression. Oh boy, right? You thought you were done with that. Well, you kind of are. But it keeps going, right? If you wanted to, you can. So the example that we're working with is in 1966, Cyril Burt published a paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart, ? The data consists of IQ scores for what we're going to assume is a random sample, but even though that's not probably the case, right? But it is one of our assumptions, and so we're assuming that it is. Right? For 27 identical twins, one raised by foster parents and the other by the biological parents. Things they could do in 1966. Wow, it's crazy. So we've got foster IQ and biological IQ. Foster IQ is on the y-axis, right? And the biological IQ is on the x-axis. Which means that in your Excel spreadsheet, right, you would have your bio IQ in one column, and you'd have your foster IQ in another column. I'm just highlighting that because you can find the mean of each of these. You can find the standard deviation of each of these. you would have the ends. The ends should be 27. That's all I know for each of these. Because you should have 27 dots. But also the correlation, you could calculate the correlation between X and Y. So if you have your data set like this, you could calculate these things, and those are the components excluding the ends. You don't really need those. But those are the components that you would need in order to calculate the slope and the intercept by hand, right? But if you're working in Excel, most likely you'll just use the Excel function, which produces the regression output. And so what that looks like, oh, look, the correlation is on here, 0.882. I don't have anything else though. That's okay. I only slashed that one because we're going to work on this one. They're the same. So Excel generates similar output to this. And what we're going to focus on today is these coefficients, right? These are estimates for the coefficients, an estimate of the intercept, and the estimate of the coefficient of bio-IQ. And so what we can do is from here, we can write in general, y hat is b naught plus b1 times x. Y hat from up here is the predicted Foster IQ, right? Because that's on our y-axis. And so this would be the Foster IQ hat, the predicted Foster IQ. The intercept, we're told, is 9.20760, so we don't have to actually calculate it. That's nice. 9.20760. And then how you read this is, okay, 0.90144 is the coefficient of the bio-IQ, which makes it the slope. And because it's positive, plus 0.90144 times the bio-IQ. Notice that that's your X and this is your Y. So instead of calculating it by hand, right, this regression equation, I make you do it because there's kind of it's easy marks is why I make you do it. Right, getting you to calculate things should be easy marks, and usually it is, and so that's why I keep it there. Otherwise, I could switch to just giving you the output, right? But you should be able to look at this output and construct your regression equation as well. Notice that we have a standard error of an estimate, right? This is my estimate for the slope, and this is my estimate for the y-intercept. Now, most of our analyses or inference for regression will focus on the slope, right? And so we're going to be working with the slope. And so we have a standard error for our estimate of the slope. And if you think about point estimates, right, what's a test statistic? And maybe I need to wait until the next slide. Fine. Fine. You're going to use the multiple r squared as your r squared if you have to. There is also an adjusted r squared, but with only one value of x, then you can just use the multiple r squared. Which of the following is false? An additional 10 points in the bio IQ is associated with an additional 9 points in the Foster twins IQ. And so 10, if I multiply by 10 here, then I get 9, which is added to the y-intercept. And so that would be true. Right? Roughly true. I'm using the one where it's highlighted, the false one. So let's talk about why the other ones are true. The linear model is Foster IQ is 9.2 plus 0.9 times the bio IQ. Well, we did it more thoroughly, but yes, that's true. Foster twins with IQs higher than average IQs tend to have biological twins with higher than average IQs as well. Why is that true? So I have a positive slope, right? They're increasing together. So why is this one false? Roughly 78%, which is referring to the multiple r squared here, roughly 78% of the Foster twins IQ can be accurately predicted by the model. Well, that's not the interpretation of r squared, is it? Is it? No. No. Since r squared is roughly 78%, we can say 78% of the variability in Foster IQ is explained by the regression equation. Oops. On bio IQ, which is not the same thing. Accurately predicted by the model? No. We're talking about how much of that variability is being captured by this model. The remaining, right, percentage is outside factors, right, not related to the bio IQ. Oh. What I tried to get into, now I will. Assuming, and that's a big assumption, that these 27 twins comprise a representative sample of all twins separated at birth, maybe. We would like to test if these data provide convincing evidence that the IQ of the biological twin is a significant predictor of IQ of the foster twin. And so what that stems from is if you have no relationship like this, right? Or let's see here, the bio IQ is on the x-axis and the foster IQ is on the y-axis. If it's just a cloud, right, then in this case, a cloud of data says bio IQ is not a good predictor of Foster IQ. Forster IQ. Yeah. Okay. Because, why? The slope here would be 0. That would be my line of best fit. It would be a slope of 0. Nothing's happening here. You can put in a very low bio IQ and get the same predicted value as if you put in a very high bio IQ, right? And so that's what makes it not a good predictor. I was going to say a bad predictor, but not a good predictor. Versus if we have something and we saw, well, we have the scatter plot. This looks like bio IQ is a good predictor of foster IQ, right? And so what we want to do is we want to test that. Oops. Versus if you have your bio IQ and your foster IQ, and you see something the slope is not equal to 0. All right. If the slope does not equal 0, anything except 0, right? If it's significantly different from 0, then, bless you, then bio IQ is a good predictor of foster IQ. Drawing on what we know about hypothesis testing, right? Hypothesis testing has to be about parameters, right? It has to be about the population, because you can find out whatever you want to find out about the sample. It's right there. You can just find it, right? And it's final, right? But what you're really trying to learn is you're trying to figure out, okay, well, what does the population look like? And so kind of first strike here, both A and C are out as options for my null and alternative hypotheses because they're just about B0 and B1, but that's from my sample. I can just find those, right? I know if it's 0 or not. Then beta naught, that's the population y-intercept, right? Which we can do hypothesis testing about, but it's a lot less common because we know lines, they just cross at some point. And so unless it's kind of a specific case, right, then usually that's not what we want to do hypothesis testing about. What we do want to do hypothesis testing about is if beta 1, the population slope, you have to assume it is 0 until you have proof that it's not. Same exact thing that we've been doing with all our hypothesis testing, right? You have to assume that everything's the same, nothing's changed until you have proof that they are different, right? So you have to assume that things look like this until your data tells you, oh, actually, you're okay to assume that you have some non-zero slope, right? There is some relationship here. And usually we only do two-sided tests for the slope, right? Because whether it's positive or negative, the slope itself will tell you. So, and maybe I'll keep this one. Recall, oops. Step 1, state the hypotheses. We said our null hypothesis is that beta 1 is equal to 0 versus our alternative hypothesis that beta 1 is not equal to 0. Step 2 of a hypothesis test is do the test, which is really calculate the test statistic. But I like do the test better. Now, a test statistic in general is your point estimate. This is true if you explore your formula sheet, right? It's going to be true for all test statistics, right? Your point estimate minus, bless you, 'tis the season, your hypothesized value divided by the standard error of the point estimate. What's nice is with our regression output, right, we get our point estimates and we're focusing on our slope. We also get the standard error of the point estimate. They've also calculated our t, which is our test statistic. What's really neat is we know how t behaves, right? We need to know the degrees of freedom, which we're not going to dive into, but it's in the slides. But just know that it follows a t distribution. And the reason we can ignore the degrees of freedom is because it also gives me the two-sided p-value, right? And so here, this is my test statistic. And this is my two-sided p-value. One for the intercept and one for the slope. And if I'm focusing on the slope, that's the one I want. You can try it. T would be the 0.9014 minus, how far is it from 0? Your hypothesized value for the slope, divided by 0.0963. And I really hope it becomes something like 9.36. Divided by 0.0963. Phew. 9.36, blah, 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 blah. But that's given to us. So we don't even need to do any calculations, right, for step 2, which is really cool. On a page here. But you can. I just wanted you to see where it came from, right? And so step 2, from the output, T is 9.36. That's really large, right? It doesn't matter what degrees of freedom you have, that's going to be really large, which means you are likely rejecting the null hypothesis. Right? Step 3, find the p-value. From the output, the two-sided p-value is roughly 0.0000. It's not 0, because there's always some probability, right? Because you'd have to get to infinity to say it's 0, right? And so it's very, very small. Right? From the output, the two-sided p-value is less or approximately 0.000. Very small. Then you can state your conclusion. Right? With a p-value this small, I have enough evidence to reject H naught. Step 4, your conclusion. Since same structure as always, right? Which is why we worked so hard on our conclusions and kind of finessing those conclusions, because they're always the same, right? They always follow the same structure. Since our two-sided p-value is approximately 0. It's not 0, it's approximately 0. It is less than our assumed alpha level of 0.05, which means we have enough evidence to reject H naught. Which means we have enough evidence to reject H naught. And if you're rejecting it, you can say in favor of HA. You don't have to, right? If it kind of bogs you down, but in favor of HA. Therefore, well, what was our null hypothesis? I reject this in favor of this. Therefore, right, there's enough evidence to say that the slope is significantly different from 0. I'm not committing to anything beyond that, right? You would have to do more testing. Okay? But therefore, the slope is significantly different from 0. Which means BioIQ is a good predictor of Foster IQ. Nice. So if you do keep going in stats, what you'll find is that really all you need is for any new hypothesis test that you come upon, right? Well, what does my data need to look like? Of course. But then what are my null and alternative hypotheses? And what's my test statistic? Right? And then from the test statistic, you would find the p-value following whatever distribution you're using. But then your conclusion always follows that same structure, right? And so really you only need these two things for a new test, and then you're off to the races. And there are a couple more slides, but I think you deserve some stickers. We'll talk about them, but that's there. I'll go as fast as I can for completeness only. But kind of a fun way, well, for me, to tie back to inference, right? Back to hypothesis testing, but in terms of regression. And so, of course, they're all related. Any questions about that before I zip through the rest of the slides? Just so quick. Oh. You won't even feel it. So, like we said, calculating the test statistic, blah, 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 blah. It does talk about the degrees of freedom. It's n-2. Okay. I can't resist because we're estimating the intercept and the slope there. So the number of things that you're estimating. And then there's an example that I don't really care about. Anything else? Oh, you can make a confidence interval for the slope. Surprise, surprise, surprise. I know, right? Because what's a confidence interval? Point estimate plus minus a critical value, right? Which in this case would be a t at n-2 degrees of freedom, so 25 degrees of freedom. You know how to find that using the t-table, right? Times the standard error of the point estimate, which you also have from the output. I'm not going to make you do that though. And then that's it. That's the end. Quick and painless. All right. Any questions? Before I officially congratulate you on sort of finishing the course. Still a minor final exam to go. But as I said, if you have any questions, you hopefully know how to find me. And good luck with your other exams. And I'll see you on the 16th. Yes. There you go. Oh. Like, oh.